Thank you for joining in and being a part of this evening. This is Swapnil Chodankar on behalf of TCS iON, and I welcome you all to this exciting webinar, which is Facets of VLSI Design. So over the past few days, we've been exploring the fascinating world of VLSI chip design in collaboration with IIT Hyderabad and TCS iON. The interest and the participation from learners across the country has shown just how much curiosity there is around this domain. From devices that we use every day, like smartphones, wearable laptops, smart home appliances, to critical applications in healthcare, automotive, and even space technology, VLSI is at the heart of modern innovation. But while the demand for skilled VLSI professionals is growing rapidly, the industry and academia gap continues to remain a big challenge. This is where the certificate program in VLSI chip design makes a big difference. Designed to build the right foundation, bridge this gap, and prepare learners for real world opportunities in the semiconductor ecosystem. Now, in today's exclusive session, we will cover the growing demand and the career scope in VLSI, why this program is a unique opportunity compared to traditional courses, and the tools, the modules, the hands-on learning you'll get as a participant, and how will this program help you launch into the booming semiconductor industry? So whether this is your first session or you've been with us in the earlier ones, I welcome you today. And you're in for a discussion that's both practical and inspiring. Now, it's my pleasure to introduce our expert speaker from TCS who brings deep industry experience and insights into the future of VLSI. We are joined with, his name is Chigapai Hari Arjun, and who brings over 15 years of experience in SOC and IP verification, emulation, FPGA solutions at the VLSI Center of Excellence. He has contributed to TCS file patents in securities trading systems using FPGA and HLS flows, and was also part of the team that designed and verified India's first microprocessor. He has deep expertise in FPGA, ASI, ASIC, and SOC design life cycles, UVM based verification, and strong hands-on skills in systems Verilog, VHDL, HLS, and C++. Over the years, he has led key projects in network on chip, PCLE, SOC connectivity, and high performance verification, along with extensive work on emulation and rapid prototyping. An engineer at heart and a research in spirit, he holds a B and a BTech, MTech in electronics, and he's currently pursuing his PhD in reusable SOC verification methodologies. So it's a pleasure to have you with us, Hari. A lovely introduction that you have, so much of experience. It's a pleasure to have you.
Thank you. Thanks for that quick intro and for those nice words. I am glad that I've got an opportunity to connect with you all. Hope we'll have an engaging session, and looking forward to complete this with all the enthusiasm that the participants.
We've got a lovely audience. In fact, they are so responsive. They've already started responding in the poll. So let's quickly dive into the session. I'll ask you my first question, Hari.
Sure, please.
So many students have heard about VLSI, but not everyone fully understand it. So my question to you, could you help students understand what is VLSI design and why semiconductors are suddenly such a big thing in the market today? Over to you.
Right. See, I think it is a very valid question in the current context. See, if you see the slide that is being shared on the screen, on the dynamics of the economics in that perspective, if you see the market is actually growing pretty big. If you see the statistic and workloads on the domains, for example, the AI, the data center kind of an expansion. And if you look at domain workloads like 5G, IoT, and combination of these two, for example, AI plus IoT, they call it as AIoT. So what is happening is the demand for the workloads is actually evolving wherein it is having a proportional impact on the size of the hardware which is supposed to be compatible for it, which is actually the primary reason why there is a lot of emphasis on VLSI today. Let it be in terms of the way in which you process a given workload in the most efficient way, or in terms of the domains that are evolving, and the kind of dynamics that I spoke on the economic side. Given all these proportions, VLSI suddenly is a very big thing. Let me also take a very simple example to understand why this is actually booming so much today, which is having a lot of traction. See, take a basic example of a mobile phone that you use, okay, which is the best example for VLSI device today, okay? See, if you break down the way in which you communicate with the mobile phone, we are the user, and eventually this is the hardware. The phone that you use is the final hardware. If you break down the stack in which the communication happens, user, then the user interface, you have all the applications on the phone. Below that, there are two operating systems which we all talk about. It is either Android or the iOS, correct? And below that is the actual hardware. Now, what is happening for the last 30 to 35 years, where the software has been really booming, there was a lot of market around software. You look at all the applications that are developed on the mobile phone. So if we have this much of timeline where there is a lot of revenue traction, etc., on the applications itself, think about the layers below. For example, the OS that is called as embedded layer, and below that is the hardware layer, where we VLSI engineers actually are part of it, right? Where the workloads and applications are growing and the workload is actually becoming so complex, eventually the need for having a compatible hardware is proportionally growing so exponentially. So that is why there is a lot of boom and where there's a lot of buzz around the VLSI today.
Thank you so much, Hari. Thank you for the insight, and it really helps students connect with why VLSI and semiconductors matters today. Like you gave a simple example, yet it means so much, a mobile phone that we use. So thank you so much. Now, all of you must have, now this is to the audience, all of you all must have heard about the software development life cycle, or SDL, the process that guides how software is designed, built, tested, and delivered. But did you know that hardware, especially in the world of chips and circuits, also has its own development life cycle? Just like software, hardware too goes through step-by-step process before it becomes a final product that we use. So my question to you, can anyone tell us what this hardware design life cycle is called? And are you familiar with the flow of the VLSI design life cycle? All right. So somebody says create, somebody says design, simulate. Yes, I know VLSI flow. Okay, that's great. If you know, then just type in what is it. Physical design flow, VLSI design flow, software development. So thank you so much for your responses. Uh, so let me ask you, Hari. As you are someone who's closely connected with the corporate world, could you share how the demand for VLSI professionals is growing? And with India investing heavily in semiconductors and chips design, what opportunities does it open for our students?
Sure. I'll probably explain this life cycle, right? Basically, because that was the question asked, and I believe this will help us gain a comprehensive understanding of how this life cycle is, and I'll also pitch in quickly into the opportunity space as well.
Wonderful. Yeah, sure.
So whatever you see on the screen, so this actually is a pictorial representation of the overall life cycle. So just like how we get to hear software development life cycle, for example, all the applications that you see on your mobile phone or on your laptop, all the applications that you see, the development life cycle adheres to what is called as SDLC, software development life cycle. Analogous to that, we also have what is called as hardware development life cycle, but we don't call it as HDLC. We call it as silicon tape out. This is a typical nomenclature which is used in the silicon engineering space or VLSI space, which actually starts from the architecture phase till the validation phase. Again, this is in fact broken down into multiple abstractions, which I will be talking about in the further slides. However, just to break it down and give a comprehensive understanding of what this tape-out life cycle is, see, for example, you wanted to come up with a mobile chipset. Okay, you are probably Qualcomm's or MediaTek's of the world, right? So you wanted to come up with a mobile chipset. So you will initially put your idea. So eventually, this is all about a process of converting concept to silicon. In fact, that is the same word, which is the same name is actually used by Government of India as part of Indian semiconductor mission today. So you ideate something, then you put it in a paper and formulate it in the form of architecture. That is the first step, all right? And then just like how there are software development languages like C, C++, you term them as HLLs, high level languages, okay? Just like how you have HLLs for software application development, for hardware development application, you have HDLs, hardware description languages, okay? So you use those hardware description languages to design the hardware in a soft form, basically, okay? I will talk about those forms in the next slides. That is done using the HDLs. Just like how you actually perform software testing in software development lifecycle, here also you perform a lot of testing, but it is not called as testing. We call it as verification. We call it as verification. And this is something which actually occupies 70% of the overall life cycle, the time, cost, and effort. This is quite data compute intensive, this verification activity. And there is a lot of thought process that actually flows in to see that you verify the chip or the design, which is meeting the architectural specifications you have captured initially. And unlike the hardware, unlike the software development activity, what also is very important here is cycle accuracy. It is not just important to check whether the applied input is coming out after processing, but also the timing. When have you applied the input? What point of the time it is being applied? How long has it been applied? When is the output coming out? And how long is the output being fetched? So this is called timing. Along with the instruction accuracy, timing is something that we have to validate, which actually makes it a bit complex, unlike the normal testing process, which is part of the software development activity. All right. So till here, from the architecture till the design verification phase, this is called front end. So you must have actually seen a lot of institutes, which publicize that we offer front end design verification course. So these are the areas where these are actually being kind of targeted. And if you look at Indian semiconductor market, where many of the semiconductor companies have their GCCs opened in India recently, but earlier, if you see, majority of this work before the establishment of the GCCs were outsourced to Indian services. For example, TCS. We work for multiple MNCs on the semicon space to get this architecture to verification. This is where we say that the design is freezed, and then this is where actually we start the physical entity of this chip being manufactured, where your fab house, your fabrication house, your OSAT house, all that comes into the picture. Eventually, there are three different phases or three different houses through which your silicon tape out happens. One is a design house. Number two is a fab house. Number three is an offshore semiconductor assembly and testing, OSAT house. For example, as far as Tatas are concerned, TCS, we are a design house. The Tata Fab, which is coming up in Gujarat, is a fab house. And the Assam OSAT is an OSAT house. As part of Tata, fortunately, we are a one-stop shop for all the silicon tape-out needs. So basically, netlist, if you see the netlist phase, this is an intermediary between the front end, basically the soft entity, and the actual physical entity that you see as part of the silicon tape-out. Then you start from the back-end activities, basically called as physical design, place and route, etc., and tape-out and validation. See, you must be thinking verification and validation. I mean, they both look ambiguous, like what is the difference? Verification is something that you carry out on a virtual software, whereas validation is a testing that is carried out on hardware. See, you are not you are not actually designing something that you experience, but you will see a physical outcome of what you design and develop here. Okay. So whatever design that you are trying to develop, right, as a chip, as an IC, as an integrated circuit, if you have to manufacture it in bulk, you don't do it at the first stretch. You first validate it and find out if it is actually working on the hardware. So there are some platforms to validate it on the hardware and check, yes, this is actually working functionally as per expectation. So that kind of a testing that is carried out on hardware is called validation. The same testing of on the design, which is carried out in a virtual tool or a virtual experimentation based modeling, is called verification. So on a whole, this is how the silicon tape out life cycle is. Okay. So if I have to quickly segregate, A to DV is front end, PD to V is back end, netlist is called as the design preparation phase, or in simple layman terms, you can call it as an intermediary between your back end and front end. See, this is actually setting the ground for understanding what are abstractions, which I'll be talking about further. All right. Now I'll come to your question. What are the kind of opportunities that are actually available on the VLSI space? In fact, I have a detailed slide which talks about the breakdown of the whole VLSI, how we have different activities and sub-level activities as part of the VLSI design lifecycle. So yeah, if you see the slide that is actually being flashed here, see, eventually we are talking about what hardware development, not software development, hardware development. Okay, there are only two kinds of hardware. Let me explain at the outset. Basically, these two hardwares are ASIC. ASIC stands for application specific integrated circuit. Okay, ASIC. And number two is FPGA, field programmable gate array. To understand what these two are, let me just go back to the good old days where we had compact discs and DVDs. You remember? See, there used to be a rewritable DVD, and there used to be one CD which once written, for example, there used to be a software called Nero where you burn some data, you can't change it. You can't change it, right? Just like that. There is a hardware where you are intending to create that IC for a specific problem statement, but you can't change it later, which means an application specific design. So that's actually called application specific integrated circuit. You port one design and tape it out, gone. Even you can't change it later. But if you want to electrically program it and rewrite the functionality, for example, today it is an addition that hardware is doing, but you wanted to modify it and to make it support abstraction division also. I'm just taking a very simple example. No, not creating a chalk and around. So for that case, you will have to go for a hardware called as FPGA, field programmable gate array. See, the electrical and physical characterization of these two hardware components is different, but eventually both are hardwares. Okay, so the life cycle for a reprogrammable hardware and for a fixed hardware are different, which are shown in this diagram. Okay, and basically the whole game of this VLSI design evolves around two operations, whether you write or read. Actually, you either write some data. See, eventually it's all about data. There is a lot of data about data called metadata. So how do you store this data in a device? How do you access this device? So for example, if I wanted to talk to you, there are two scenarios. I am the source. So you are one node, you are one source. I am a destination. If you wanted to talk to me, is you write data, you are source and I am the destination. For example, you wanted to know some data from me, is a read operation. All right. Eventually, the whole game of this VLSI is all about this. But when to do write, when to do read, right, is based on some phasing, and this is done as per some protocol. Protocol is nothing but standard set of rules which ensures standard exchange of data between two nodes. That is of two types. Okay, it can be standard or customized. So if you see the diagram there, so I have to set this context to make you understand what is custom, etc. That's why all this verbal explanation. So if these are standard protocols like PCIe, Ethernet. These are standard protocols. It's not that somebody has to define it. They are already defined and standardized. If you have to build an application specific integrated circuit just with these standard and some limited number of you defined, custom defined, for example, TCS defined or Harinagarjun defined, custom. So that is called, a combination of these two is called semi-custom design. If it is totally customized, you don't have, you wanted to come up with a low cost solution where you define your protocols, you define your standard, you define your own interfaces, nothing standardized, that is called full custom flow. All right. So that is what it talks about. Eventually, this is how your application specific integrated circuit is designed and developed. And when it comes to FPGA, it is kind of linear flow. It is not discrete. It is not divided into two different places where you have custom, standard, etc. It can be anything, but the flow is linear, where you have to just there are limited set of vendors and limited set of proprietary flows that you need to learn, and you can port the design and program it. But whereas the ASIC, application specific integrated circuit, you have to go through a process called as fabrication, OSAT, everything. All right. So this is what this particular diagram talks about. Something like I think I pretty well explained what is full custom, semi-custom, etc., etc. In the further slides, you will get more insights about it. All right. Maybe we can just navigate to the next slide, and I'll also get into the insights of what different opportunities are available here. See, this is the pictorial representation or the hierarchical breakdown of how the opportunity space in VLSI is. So if you see the pictorial representation, which is flashed on the screen there, see the overall VLSI is, in terms of opportunity space, is broken down precisely into these things. ASIC SoC design. SoC stands for system on chip. SoC is a system on chip. Okay. Eventually, your ASIC or FPGA will be an ASIC, an SoC, system on chip. Okay. That's the nomenclature, or else it will be an FPGA design. So just like how you have IDEs, integrated development environments, which are used for software development, in hardware, we don't have IDEs. We call them as EDA, electronic design automation, EDA. Okay, there is a lot of space, opportunity space. In fact, a lot of market traction on the EDS. Just to tell you, there are only 3 players. For example, in software, there are a lot of commercial and non-commercial players. In fact, there are tools which are available in open source. But in hardware, no, there are only 3. For example, Siemens, Mentor Graphics, Cadence, Synopsys. Only 3 players. And these are all Fortune 100 companies. And they are literally doing a lot of monopoly there. Okay. And these tools are all very costly. Okay. None of them, forget about the tools. Even some libraries are not open source. So they are all proprietary. And there is a lot of work that you have to do to purchase these tools and customize it for your application development, your hardware development. Somebody, for example, Qualcomm's of the world work on mobile chipset development, Intel's and NVIDIA's and AMD's of the world work on server chipset development. Okay, so they customize the EDA framework for them. So there's a lot of work which actually gets carried out there, and there are a lot of opportunities lying there. So first 3 are on the front end, pre-silicon part on the design house. All right. Now comes the manufacturing, where we have a fab coming up, and there is a lot of validation that I spoke about in the earlier slide that is carried out in the OSAT phase. So at a high level, this is the breakdown. Now, if you further breakdown, you can actually compare it with the earlier slide. I spoke about front end, back end. I also spoke about the design house, the fab house, and the OSAT house. Precisely, if I have to demarcate, the ASIC, FPGA, EDA, it's all part of the design house related opportunities. Manufacturing more at a fab house, custom design more at an OSAT house. This is how the breakdown is. By the way, I come from front-end design verification. I am a pre-silicon design verification architect. And I am part of the first hierarchical path that you see, the front-end architecture, microarchitecture, a logic, RTL design, verification, etc. That is where I come from. And this is where 70% of the time, effort, cost lies within. In fact, the opportunities also, let me tell you. Okay. So this is on the front end part. I thought it is pretty good to actually capture one slide, like what all companies, which are a combination of services as well as product companies which are there in our country. In fact, you can see TCS also there. Tata Group, Tata Elxsi, as well as TCS are offering services on the VLSI space. And you can see some of the major semiconductor players like Intel. You can actually see on semiconductor, AMD, Cadence. I spoke about Cadence, which is an EDA major, etc. So these are all the companies which are actually offering a lot of job opportunities in the VLSI space across the life cycle. Okay, a few of them are specialized in offering only front end. A few of them are specialized across the life cycle where there are multiple job opportunities which are offered. And I just wanted to tell you one thing. Unlike the software industry, this is one industry which is a core opportunity with a niche skill set, niche kind of a skill set where opportunities are more, but limited number of talent pool. That is the challenge. In a contrast where software, for one opportunity you have actually hundreds of people waiting outside to grab it, right? So, but the challenge is getting an entry here is definitely difficult. I'm not trying to talk about the soft side of it, but the hard side of it is you need to be very strong in terms of what you study during your academics. And unfortunately, there is another gap, to be very honest with you. The academic curriculum for both graduation as well as PG level, at least for majority of the institutes in India, are not aligned to the industry needs. So I believe this is where our coursework can actually bridge the gap, help them bridge the gap, and set a stage to open the horizon for getting an opportunity in the VLSI space. Yeah, I think that's pretty much about it. Maybe.
Wonderful, Hari. Thank you so much. It was really nice where you made the pictorial representation, and you've put in so much of effort to show how the life cycle flows, and then all of this, which is really nice. Thank you so much. I'm sure most of our attendees must have related to it. Thank you so much. In fact, we are getting so many questions. Relevant question which you already spoke about. Deepak Kumar says, I just wanted to know if learning this skill will land me a decent job, unlike software engineer, where there's high competition. So you already answered it. So there's a lot of scope in this field. It's only that skilled professionals are lacking, right?
It is. So, absolutely, that's true.
Now there's another question. In fact, Abhinaya asks, present currently in the market, which is the demand? Is it for front end or back end? You spoke about the life cycle, I believe. So I think that's what Abhinaya is asking.
Conventionally, even the current scenario of Indian semiconductor picture, if you consider that, see, we are on the way to get our first made in India chip, where we have our own fab, etc., coming up. Even in that scenario, conventionally, if you look at the silicon tape out life cycle, irrespective of whether our nation has the fab house, manufacturing house or not, like I mentioned, 70% of the time, 65 to 70% of the effort, time, cost, and the opportunities lie within the front-end design verification space. Honestly, that's how it is. I think that pretty well answers your question. If you also have to understand which particular skill set helps me fetch more package, that is also front-end design verification.
That's where you are, Hari, right now, in the front end. So you're at the right spot. Yeah. Wonderful. Thank you so much. Let's move on. We've got a lot to cover. So
okay. So before actually talking a bit about the pictorial representation that is being flashed on the screen, so see, right from your first year of your graduation, when you are made to do some coding, right, you'll sit in front of a computer and you will be given access to a Turbo C or a GCC kind of a compiler. And somebody might ask you to convert a piece of a problem statement into code. Am I right? So what is the final outcome there? What is the final outcome there? So you write a piece of code for a given problem statement using a language like C, C++, Java, whatever it is. So what is the final outcome? Final outcome is again an EXE or a binary. That's all. So eventually what you see is what you get. You only see, you can only experience the final outcome in what is called as a soft form. Okay, all right. So we generally talk about, do you have a soft copy or a hard copy? Hard copy is something which is physical. Soft copy, which is in the electronic form, all right? So basically these are two, this is what abstraction is all about. What is the form in which the development or the final outcome is? Here, we start, unlike you consider the software development life cycle, you start from a soft level of abstraction where you write a code, and the life cycle ends in soft form of abstraction. You don't carry it something physically as a prototype with your hand, right? So you only experience it running it on a hardware eventually, right? So the life cycle starts in a soft form, ends in a soft form itself, but which is not the case in hardware development life cycle. It starts from this soft form where the development actually starts using some HDLs, like I explained in my earlier slide. Eventually, it translates to what is called as a net list. Net list. If you have studied the basic digital electronics, you must have heard of what are universal gates, the NAND and NOR gates. Okay, so this piece of code that you write in HDL, either VHDL or Verilog, translates into what is called as a net list, which is an intermediary. This is given as an input to your manufacturing house called fab. That will yield a final outcome in a physical form. That is a hard form. So there are three abstractions here, unlike the software development. Soft form, the intermediate form, which is called as netlist. Third is a hard form. That's why all the semiconductor IPs, eventually we are all talking about intellectual properties. Semiconductor IPs are categorized into three types: soft IPs, firm IPs, hard IPs. This is what abstraction is all about. See, this is important in the current context of getting an entry. So whatever abstractions that are shown on the pictorial representations that are shown on the screen, you can actually see some piece of code which is actually being translated into some waveform. Let's not get into the details, but I'm just trying to explain that it is just a virtual software or a virtual tool that runs on a platform as a platform, and it is all in the soft form of the abstraction. So that is all dealt with a phase called simulation. You must have heard about it during your software development activity also. In your first year of graduation, you could have written a piece of code in C, Turbo C, etc., and you simulate it, right? Your faculty or the lab instructor will ask you to please convert the piece of problem statement to code and simulate it. It's all something which you experience. Again, what you do here is you translate it into a netlist and you port it on a hardware to check whether it is functionally working fine or not. If you remember, I spoke about FPGA in the earlier slides. So here, even before you arrive at an actual engineering sample, the actual IC, integrated circuit, in order to check whether it works fine on the hardware or not, you prototype it on FPGA. FPGA is available at lower cost, but if you have to tape out ASICs, it requires billions and millions of dollars. So that's why even before bulk manufacture, you port it on a hardware and you validate it. That testing is for that. So this is where your form abstraction comes into the picture. And finally, I spoke about an element like instruction accuracy, timing accuracy, right? Cycle accuracy. How much of time you are applying the input and how reliable is the output being triggered, etc. So you validate on a platform which exactly mimics the timing as well as the instructions in a platform called emulator. The name itself suggests it emulates the actuality of the IC once it is taped out. So basically, these are three different platforms that target three different abstractions and their respective validation. So from this figure, you must have not only understood the significance and the segregation of the abstractions, but why verification and validation alone consumes a lot of time in the silicon tape out. You must have understood. This is extremely data compute intensive. This is quite laborious actually, right? So this is pretty much about the abstractions. I hope I've given you a proper picture of how it is. If you have any questions, I'll probably be able to help you here. Yeah.
Sure,
Let us move
we've
on.
got a few questions, but I personally want to tell you, you've got an impressive way of explaining things, and it's really nice. You put it across in a very simple and a precise way. Though, there's so much to it, but the way that you're explaining is awesome. So thank you so much. how about designing a SC V processor, same like AMD EPYC processor? I want to work on that. Tell me how, and please, if you can give him some more information, Hari.
Sure, definitely. This question is quite specific, and yeah, your question is with respect to a RISC-V based architecture in contrast to the AMD's EPIC. By the way, our team, in fact, I was the lead for one of the module level development at AMD, is one of our clients where we work for. So, both are two different perspectives. RISC-V is an open source architecture. Of late, there has been a lot of efforts that have been put forth to democratize the chip design, actually. All right. So RISC-V is one such initiative. Just like how you have microprocessors which are proprietary, coming from the AMDs, Intels, and Qualcomms of the world. RISC-V is an open source architecture. Basically, there is something called as compute architecture and instruction set architecture. I'll not get into the details there because it might create a jargon, but these are divided into two different perspectives. One available as open source, the other which is available as proprietary, where you have to pay some fee, licensing, etc. Okay. EPIC is completely proprietary, right? If you have to arrive at utilizing RISC-V and developing EPIC, AMD's EPIC kind of an architecture, it is a long way to go, but there are possibilities, and you need a big team. You probably have to come up with a startup on your own, right? You might probably have to seek a lot of funding, but if you have a proper ideation to to create the concept to silicon, I think, in fact, Government of India today has rolled out a scheme for such initiatives called C2S, concept to silicon, the design linked incentive kind of things. I suggest you, in fact, come up with a team, properly try to formulate it, put it in a paper, and submit the proposal. Answer is definitely yes. You can use the RISC-V architecture, which is open source. There are multiple forums available in the open source where you can post your queries, etc. And in fact, IIT Madras, based out of India, where we in fact are collaborating closely with them to develop India's first indigenous microprocessor, which is in fact RISC-V based. There is a lot of traction around RISC-V, and it is possible. And I'm also giving you an insight. If you can build a team, submit a proposal. In fact, there are very good chances that you might get seed funded. Okay. Yeah.
Wow, Hari, thank you so much. This is really nice. So, your Lalit, I'm sure you must have got your answer, and you must have also realized that, the way that I pronounced it, epic, that's what Hari said. I wasn't sure about it, but y'all have got this opportunity. Y'all can ask as many questions to this expert, and I'm sure y'all will get all your answers today. So another question for you, Hari. Deepak Kumar says, how many months will it require to learn the basics of VLSI? It's a very good question.
See, there are a couple of perspectives to it. First of all, let us understand what are the prerequisites. So I'll answer this question in two different ways. Given these prerequisites already covered, there is a timeline that we have to look at. These prerequisites not pretty well familiar with, then there is a different timeline that we have to consider. Okay. First of all, the eligible criteria basically here is BE BTechs, ME MTechs. In fact, the PhD is also coming from the circuit branches: electrical, electronics, instrumentation, communication. These are the branches. If you are, in fact, I have a slide which talks pretty well about it. If you are pretty good at basics of digital electronics, Boolean algebra, the computer architecture organization, fundamentals of one hardware description language, which is generally being dealt as part of your academic curriculum, for example, Verilog or VHDL, and your basic foundation and grip on C language, if these are good, right, it probably might take close to 3 to 4 months of timeline, which in fact all the standard institutions that offer VLSI as a course, the bridge course, which will kind of help you to get equipped to be industry ready and help you to bridge the gap between industry and institute. Given these prerequisites covered, this 3 to 4 months of timeline effectively spent can help you to be kind of armed and equipped to get an entry in the VLSI space. If not, then I think there are diploma, because there are courses aligned to this. There are institutes which offer courses for 6 months as a diploma, for 1 year aligned along with some internship, And in fact, there are institutes which collaborate with universities like JNTUs, the JNTU Hyderabad, etc., Usmania
In
University.
fact, Hari, I'm so sorry to cut you off. We have a course itself with IIT Hyderabad, right?
Wonderful.
So that's the best opportunity that Deepak can get. So Deepak, to answer this, I'll give you a gist about it. So are you done, Hari?
I'm
I'll
done.
take them
Go ahead.
quickly.
Yeah,
Take them through the course. So Deepak, you have this question: how many months will it require? You know, you want to learn, which is very good. There's another question by Nazia Sheikh. She says, "Sir, can you suggest some books that can help us learn VLSI?" You know, we've got the best option for you all. And to explain this, I have an expert speaker with us who's the subject matter expert. His name is Pratap. So very warm welcome to you, Pratap. If you can take the audience through the course, it will really be awesome.
Thank you so much, Swapnil and Hari. Is my voice clear? Can you all hear me?
Yes, absolutely clear.
It was wonderful to listen to Hari. I have listened to his lecture earlier also, and it is a really very immersive session that he normally conducts. And today's session is no different. So thanks, Hari, for sharing all the fundamentals about VLSI, the opportunity space that we have, the prerequisites that the learners need to have. As Swapnil mentioned, we have a course designed in collaboration with IIT Hyderabad, between TCS and IIT Hyderabad. So it's called VLSI Chip Design. You can see it on the screen. It's a 2-month certificate program offered by IIT Hyderabad. It is a 40+ hours of experiential learning, and it's a online learning plus offline learning. So you have online learning for 40+ hours, which runs for 2 months, 8 weeks, and each week there will be 2 sessions. And after completing the online classes for 2 months, then we have an opportunity to do practice at IIT Hyderabad for 1 full week, full time for 1 full week, 5 days and 8 hours per day. So it's again 40 hours. So that's the opportunity to work at IIT Hyderabad under the supervision of IIT Hyderabad professors. So as part of the course, we are covering live lectures, exposure to cutting edge tools by IT professors and industry experts. Hari has mentioned tools like Cadence. So Cadence is part of the course. So those who go to IIT Hyderabad for the boot camp for experiential learning, so they will get opportunity to practice and then do some design using Cadence tool. And a boot camp will come up with an additional cost. The details are mentioned on the certificate page. We'll show the certificate page shortly. But the prerequisite or eligibility criteria is, so you need to have some fundamental knowledge in electronics, as Hari mentioned. So electronics or circuit design. If you are from any branch with the circuit as a primary course, you are welcome to do it. But if you are a non-circuit branch, or if you are not a electronics branch student, you are free to attend all the webinars that we are conducting in this month. You can go through the recordings that are available on our website, and we will be conducting few sessions in the coming month as well. So you can all go through this, and then if you think this is the right place for you to get into, you can join the course. And it's a fundamental course. As Hari mentioned, this course will cover the basics of VLSI. Anyone can learn, but if you are from electronics and circuit branch departments, you will have an advantage. So individuals interested to pursue research in the field of VLSI also can take up this course. And what are the potential career paths that this course will offer? So Hari mentioned a lot, and he talked a lot about front end and then verification. So you can see the roles that are listed here: VLSI design engineer, physical design engineer, analog design engineer, layout engineer, verification engineer, and test engineer. These are some of the roles that you can get into, and the packages are again very attractive compared to the starting salaries in the IT field. You can expect a starting salary in a range from 7 to 20 lakhs. It depends on the skills, how you possess, how you appear, or how you impress the people during the interview. That it all depends on that. and you can see the tools that are part of this particular course: Cadence, LT Space, Mentor Graphics, and these are some of the activities that you will be doing at the end of the course. Design and then simulation of analog blocks, design and simulation of test benches, and verify implementation of digital circuits. All these things will be part of the course, and these are the professors who will be teaching you as part of the course, and they will be available during the boot camp at IIT Hyderabad as well. And this is the QR code where you can scan, and then you can go to the website for more details about the course. And the course is starting from 8th October onwards. It goes for 8 weeks until 29th of November. After 29th of November, you need to travel to IIT Hyderabad for physical bootcamp, which is an optional. So without bootcamp, the course price is 14,160, including all taxes. But bootcamp alone comes up with additional cost because it requires licensing cost of the tools and then lab space. All those things cost a little bit extra. So it costs around 8,000 plus GST, which comes to 9,440 rupees. So that's a wonderful course that we have designed for all the people who wants to learn about VLSI. I sincerely request to go to our website and then find out more details. Over to you, Swapnil.
Thank you so much, Pratap, for taking us through all of this session. So we've got Venkateshwaralu who says that can you send me the recording of this session? So the recording will be available after a few weeks. Meanwhile, you all can check our Jobinar page. The link will be posted. There are previous recordings of professors out there. And so somebody also asks, Sorabi says that, could you please tell me what kind of skills can I develop and how, and could you refer us the online course? This is that online course that we were talking about. It is a game changer for you. You can enroll for it right now. You can still see the scan code out there. Just scan the scan code. You will go to the page and you can check more about it. Jani says, I have worked for 8 months as a project associate in IIT Madras IG indigenous project, and later I shifted to prepare a civil service. I have a 3-year gap. How will this course ensure upskilling in VSLI in getting a job in VSLI field? So Hari, how do you feel this course would help somebody who's got a gap maybe in their career? It will help them to touch base upon the fundamentals. And so what are your thoughts on it?
No, I think this question to this particular participant is pretty specific here, because he already has some hands-on experience at IIT Madras. Number two, this is not like a software job where based on your proficiency in what you can do, right, is pretty much sufficient enough to secure a job in this space, because this is a core job. This is not a software job, by the way. All you have to do is demonstrate the required skills that they are looking for. I mean, the core skills that we have been. I think the most important element which can help you to get equipped to be ready for the job market is this course. Is what I believe, because I've seen the complete curriculum. This is exactly fitting the kind of gap, filling the gap in terms of bridging the industry and the institute. It is something. It is giving you a kind of an armory to get ready for the job. That's how this coursework is aligned. And more importantly, the kind of faculty members, the kind of experience that they come with is something which can help you to easily crack the technical discussions. That's how I would see that.
Wonderful. I have a question. Dhanush says, I'm a computer science student. Can I understand VLSI easily?
Yes, it is. See, it depends on what kind of a curriculum that you have gone through, because conventional courses in terms of computer architecture were included earlier in majority of the universities. I am not sure which university you come from. For example, if you take universities like Anna University, JNTU, or Usmania University, where I am kind of familiar with, these are the computer science courses also include the traditional and conventional computer architecture and digital electronics, because they are kind of foundational elements for VLSI course. If you have already covered those prerequisites, I would say it is definitely easy for you. See, nothing is impossible, but as far as eligibility criteria is concerned, yes, along with circuit branches, CSE grads with some specialization are also eligible enough to crack an opportunity in VLSI space for sure. But how far will you be suitable or not is a question that we have to answer, and that comes from whether you are aligned to this prerequisites being covered in the academic curriculum or not. That's how we should look at it.
Wonderful. Thank you so much. Wami says, VLSI chip design course from IIT Hyderabad, is it enough to get me a job? See, one thing that we can assure you is that once when you complete this, you'll get a certificate which will be a joint certificate from IIT Hyderabad, and it will be a joint certificate from TCS iON. So two giants coming together, and that will definitely give so much weightage on your resume. So, I'm sure that you'd be able to crack, and they will handhold you throughout the session. So that's really one good thing. Can you tell me about the fee details, Venkata? The fee, you can see it out there. It says 14,160. And if you go for the additional boot camp, it will be 9,440. Quite a lot to cover. What is the potential of the core electronics engineering industry? Is it a semiconductor, advanced communication, 5G or 6G, IoT, AIML, or others? If you all can also select this option in the Slido. And while we do that, Hari, I would like to hear from you. Why should electronic students retain their core engineering skills and consider VLSI instead of moving into IT jobs? We already overshot our time, but we'll surely want to hear this from you.
Yeah, I understand. In the interest of time, I'll keep this answer short and crisp. See, I will answer this question aligned to the current scenario. Given the current scenario of AI, artificial intelligence, generative AI being so disruptive on the software space, we get to hear a lot of news about 80% of the grads, including the institutes from eminence and importance, are left jobless despite pursuing their education from these premier institutes, etc. It's not their fault, but unfortunately, it is the kind of disruption which AI is creating. But then I'll just tell you one thing, okay? Eventually, from this course and from the perspectives that I just explained earlier, it is the compatibility of the hardware which will help you to process a specific workload in the most efficient way. What are we talking about? We are talking about AI, okay? Just think in this way. See, you can't create a physical entity using virtual AI, virtual. I mean, so long as the life cycle is lying within the soft form, the abstraction that I spoke about, it's quite obvious, and the rationale itself explains us that AI can easily replace it. Number one. Number two, so in contrast to the software development, it has three different abstractions where the life cycles are pretty, versatile in terms of throwing a lot of opportunities across the root level, across the branches that I've shown in the earlier slides. And this is a physical entity eventually that you have to develop. There, where your AI ML kind of frameworks can help you to be more productive, but what will not replace you. So this is kind of immunity that you get in the current situation. I mean, this is the only opportunity space that you can think of. Okay, that is one way to look at it. And number two, see, eventually you need more silicon, or you need more device, or you need complex design to process more AI. But the other way around, the statement in the other way, the vice versa is not true. You can't have more devices or more silicon by processing more AI. No, right? So that pretty well answers the question. So eventually, you need, if you are heading towards the AI ride, that's kind of going on and pretty crazily today, right? Not sure if the investments will turn out to be positive or it's kind of a boom that gets blast. Whatever the scenario it is, eventually you need a lot of device capability and complexity to go high, where VLSI is going to grow a lot. That pretty well answers the question. Eventually, you will be looking at the opportunity space where you'll try to grab an opportunity, and this is where it is. Okay, that's how it.
Wonderful. Thank you so much, Hari. You know what? I have a chat. Jani says that Hari sir's explanation and the depth of his knowledge makes us to hear more from him. So thank you so much. It's so nice, Jani, that you've posted that.
Thank you.
And it's true, Hari. It's true. I mentioned that earlier. The way that you explain is awesome. So thank you so much. Let me quickly go to the next question. From an industry perspective, what specific skills, tools, and competencies do companies look while hiring? Because that's the main question. So Jani had asked about placement. Also, Teja asked about placement assistance. So I just want to know from you that what do they look for, while hiring in the VLSI space, and how should learners focus their efforts to stand out as a job-ready professional?
Yeah, see, you should be pretty good at your basics during your academics. It's not like you study something during your 4 year of academics or 2 years of MTech, but you end up doing something else while you end up in the job. But this is a continuation in continuation to what your academics are, right? So your core basics, your academic knowledge should be strong enough. Your foundation skills, your foundation subject knowledge should be intact. That's one thing. Just to answer your question in a better way, I thought I'll first showcase what is the job description. So the one that you see on the screen is a job description, is a JD from NVIDIA, okay, for an ASIC application specific integrated circuit verification engineer, which pretty well talks about the minimum requirements in terms of the educational qualification. And below 3 to 4 points pretty well talk about the competencies, the core competencies that they look at. They were pretty well mentioning in their job description about the expertise and understanding of Verilog, system Verilog, which are generally taught at academic level, all right? But some proficiency, your understanding, your thoughts, and how to correlate this with the real-time scenarios. You have your mobile phones, laptop, desktops. Just close your eyes and open. Around you, there are a lot of VLSI. VLSI is inevitable today. You can't bypass a VLSI or a digital device. Everything, in fact, the robotic surgeries that are happening today are all VLSI-based programming perspectives, right? So everywhere it is VLSI. So you can just understand and correlate your academic knowledge to the real-time perspectives is what they generally look at, okay? Apart from the subject knowledge. So I think the minimum requirements which are captured in the job description pretty well talks about it. If you can just go to the next slide, I thought it will be of interest to you that TCS is actually offering a lot of VLSI opportunities, and it has a VLSI practice. So this is the job description which we have rolled out. This is a TCS ASIC verification engineer requirement. So in both the job descriptions, you could have seen that the requirement criteria pretty well talks about the prerequisites in terms of the HDL, the digital electronics, the basic programming perspectives of C or C++, while the eligibility criteria seems to be same, but the requirements in terms of the skill sets, are also kind of aligned to your core foundation elements we covered during your academics, all right? So I hope this pretty well explains you like what is the prerequisite, what exactly is it, right? I think I put it in the shortest form. Maybe we can probably get into a detailed discussion. I can keep on talking a lot about it, but I think at a high level, this is what it is going to be.
Wonderful. Hari, like you said, you can keep talking about it. And to be honest, we can keep on listening from you. That's what we would really, it's so interesting to hear from you. So showcase the technical insights and the real-time examples that you have prepared for them.
Yeah, I will definitely talk a bit about the technical insights. So, I thought I'll quickly take an example of your mobile phone itself. You might be wondering, so you actually touch your mobile phone because most of them are all sensor based. You might be wondering, like, what is the typical response time for an input that you give and the response it gives back? Technically, it is termed as a turnaround time. I wanted to share a very quick example, but before that, if somebody can actually answer the earlier question, for example, if you have considered the digital device that you have noticed around you is a mobile phone, can someone please type in the chat window what frequency? See, generally when you purchase a mobile phone, you look at the memory, how much of on-chip memory it has, how much of expandable memory it has, and by the way, speed of operation. Even if you are a layman, you will definitely ask, boss, I am giving this much of money, how fast will it actually work? So can someone please type on the chat window, what is the frequency, what is the bus speed of your mobile phone? Anyone? See, I hope 9 out of the 10 participants could have probably had the mobile phone in your hand. It can be an Android phone, or it can be an iOS phone, it can be Oppo, MI. Don't worry about it. Please type the bus speed of the mobile phone that you have purchased, the one which you have. I will give you, no, not in GBs. It will be in heads. It will be in gigahertz. GB is okay. 4, like 2 to 3. Wonderful. No, 700 gigahertz. No. It will be in 2 to 3 gigahertz. Okay. Let me tell you a quick insight. Let me let me actually help you to do some math. Yeah, in megahertz, somebody said it is 2 to, okay, consider it as 2 gigahertz, 2 gigahertz, okay. Let me help you. I just made a statement that you have to correlate your academic learning with your real-time perspective, okay. Consider 2 gigahertz. And let me help you understand what is the turnaround time for your phone when you actually try to give an input and expect an output. What is the turnaround time? Okay. You all know from the good old basics that frequency is inversely proportional to time. All right. So please do f is equal to 1 by t, or t is equal to 1 by f. So 1 by 2 gigahertz. How much is it? Can someone quickly please escort yourselves and just type what will be the answer? 1 by 2 gigahertz. Giga is how much? 10 power 9. It goes up to the numerator. It will be 10 power minus 9, right? So it is nanoseconds. Nano, right? I'm just trying to calculate the time. Okay. Now it will be 1 by 2. 1 by 2 is 0.5. All right. So it is 0.5 nanoseconds. Okay. You all know everything operates on a clock. There is something called as duty cycle. Guys, I'm not talking something totally out of the box. These are basic things that you get to study during your electronics. Okay. So a standard duty cycle in any phone, basically in a standard duty cycle will be 50%. 50%. So 0.5 nanoseconds divided by 2. So it will be 0.25. Okay. So your clock keeps toggling at the rate of 0.25 nanoseconds. So the total time is t on plus t off. So 0.25 plus 0.25. Eventually it is 0.5 nanoseconds. So what have we calculated now? We have calculated the turnaround time or the response time of your mobile phone, whichever you said is 2 gigahertz, for your input that you give and the time to respond back. The total turnaround time is 0.5 nanoseconds. Have you ever thought of this? I'm just giving, I can start sharing more insights in this way. I thought this technical insight could be a bit interesting. Any questions here, I'll be happy to answer. I can in fact help you think much more in terms of the real-time application. So that's what I captured here. I don't want to bore you with so many other, explanations, etc., etc. So what is the problem statement? How do you solve it? What language do you write? What is the language you actually use to write the program? You write the same code. You convert the same 0.5 nanoseconds, toggling on and off. You write the program yourself as a self-practice in C, C++, Java, or you write it in Verilog if you are comfortable, or MATLAB. Then try to understand and break down the real-time application with use case. This is the kind of thought process that you need, along with the kind of academic knowledge at a foundation level. I thought this is a bit interesting. I kind of brought this example. So this is one exemplary explanation of how the technical insight and thought process should be to get an entry into VLSI space.
Thank you so much, Hari. After your explanation, the way that I look at my mobile phone has completely changed. You've changed my perspective, definitely. Any final thoughts, Hari, about the course and about them, how would it help them in the long run?
So all I wanted to say is, given the current scenario, VLSI is the savior. This is something which is shining through the fog. Anybody who sticks to the core perspectives were the people who are most successful in their life, to be very honest with you. I mean, there are multiple perspectives to look at it. However, this is my personal observation, which I would like to share. And just wanted to give you a statistical figure here, okay? India has 20% of global VLSI workforce. If you see, look at the designers. This is a statistical figure which was actually shared by the Ministry of Information Technology officers during one of the conferences that we have attended, Semicon India, Semicon Tantra recently. And the count is close to 35,000. 35,000. In contrast to 33 lakh software engineers working on ITES space. Okay, so if that is 20%, which is 35,000, is what India has of the global workforce. So imagine what is the global headcount, close to 1.75 or maximum 2 lakhs. That's all. But okay, this is the statistical figure. Given the scenario of more and more GCCs coming up in India and more, so we are only talking about Indian semiconductor mission, but we are not talking about the CHIPS Act that Europe has and US has. They have literally rolled out a lot of funds. You know, if you talk about the Indian semiconductor mission, 2,75,000 crores. That's a huge money in independent India, actually. After we gain independence, this is pretty huge. I mean, this is actually to make our country so robust and a leader, global leader in terms of the technology, finances, everything. Okay. Now, given this scenario, just think out, you know, the kind of need that the MITI predicts is in the next 3 to 4 years, there will be a shortage of at least 3.5 lakh engineers. See, don't consider the figure as is. Consider 1/3 of it. 1/3 of it, maybe 1.21 lakh engineers. That is also pretty huge. So given this scenario, I would advise you, rather than talking something randomly, I thought I'll put the statistical data and give you the ground reality. Think out, this is one opportunity space where lot of, openings are there, but the required talent pool with the required prerequisites are very less. I have gone through, I'm not trying to blindly endorse the course, but I've seen the course structure and looking at the people who teach you this course, this is going to be a game changer for sure, right? You can count on my words. I would definitely suggest all the participants of the session to proactively look at picking up this course, which will help you equipped for a VLSI job and get market ready. That's all I have to say. Thank you.
Wonderful. Thank you so much, Hari. Once again, it's been an awesome session. Thank you for your time. And thank you so much. I just want to wish you all the best of luck. I'm sure that you all have already clicked the link after listening to the stats Hari gave us, and you all will be in the course. So thank you, Pratap, for your time and patience with us. And for my team in the background, I want to wish you all a pleasant evening.
Thank you, Swapnil.